Hello, everyone. Welcome to the United States Geological Survey public lecture for this month. Thanks, everyone, for joining us tonight. My name is Christy Ryan, and I'm with our USGS Science Information Services Office, and I will be your host and your moderator today. Before I introduce our speaker for tonight, I have a few announcements to make. First, I want to give you a heads up about our lecture for next month. On May 27th, we will have USGS research geologist Austin Elliott on. Austin is with our Earthquake Hazard Science Center, and the title of his lecture is going to be Where Earthquakes Hide in the Desert, What We've Learned from Recent Fault Ruptures in the Western US. So please make sure you save the date and come back again next month. And just a few more tips, because this is like a new virtual platform. If you need to turn on closed captioning on your mobile device, just tap on the screen and look for the TV icon at the bottom. If you're on a desktop computer, click the screen and look for the closed caption symbol on the bottom. And just so you know, we do want this to be a little bit interactive. So towards the end of the lecture, we do want to open it up for a question and answer session. If you have a question for our speaker, you can submit them through the chat window. To find it, just look towards the top of your screen in the upper right-hand corner, and you should see a question mark, which will bring up the Q&A panel, and you can type in any question you have there. We'll do our best at the end to get through all of them, but please understand we might not have time for all of them. And so now, I want to introduce you to our speaker tonight. Dr. Michael Tischler is the director of the National Geospatial Program at the USGS. The National Geospatial Program provides the digital geospatial foundation for the United States and is responsible for designing, planning, and executing the National Topographic Mapping Program. Dr. Tischler provides management oversight and direction to the National Geospatial Program, including the National Map, the National Geotechnical Operations Center, the 3D Elevation Program, the National Hydrography Dataset, the US TopoMap Series, research activities performed at the Center of Excellence for Geospatial Information Science, and geospatial data and information in response to natural disasters, I should say. Dr. Tischler holds a Bachelor of Science degree in Soil Science from North Dakota University, a Master of Science degree in Soil and Water Science from the University of Florida, and a PhD in Earth Systems and Geoinformation Science from George Mason University. So, with that said, let's all give a warm virtual welcome to Dr. Tischler. And Mike, the floor is yours.
Thank you so much, Christine and Amelia. It's really wonderful to be here and to be able to speak to all of you about the Topographic Mapping Program, the National Geospatial Program, and how we turn data that we collect into maps. I'm really privileged to be in the position that I am, leading the National Geospatial Program. We often refer to ourselves as the nation's civilian mapping program. There are a number of people across the federal government that do mapping. We actually happen to be the lead agency at the US Geological Survey, and we've been doing that for quite some time. First, I wanted to talk a little bit about the National Geospatial Program, NGP, and what it is that we do. We provide national topographic information to advance science, support government, enlighten citizens, and enable decision-making, and that's quite a lot. I often like to say that we aim to deliver data according to the 4 A's that you see there: data that's authoritative, accessible, available, and accurate. Authoritative is a term that we use to mean that it's got a reputation and the government standing behind it. It's data that you can rely on, and is, in this case, the government is sort of guaranteeing that this data is the best data that's possible through its quality, through its accuracy, through the rigor that we put in how we produce it. And speaking of accuracy, that is something we take very seriously. We understand that USGS has been around a long time. People understand the name. And when you see USGS on a map or any other data products, people have an expectation that that data is really going to be reliable. And we live that legacy every day in the quality standards and the data quality standards and delivery and metadata and all of the work that we do across the breadth of the program to make sure that when people use the data, they can stand behind it. More recently, we have a focus on making data that's accessible and available. It does no good if we spend time and energy and taxpayer dollars collecting vast amounts of data and producing maps if it just stays in a virtual drawer or stays in a computer system. We want the data out there. We want people to use it. We want it easy to find, and we want it to be able to fit however you might want to use it. Maybe it's a paper map at a kitchen table for a camping trip. Maybe it's a high-end user that wants to use it, that wants to download our data and use it in a geographic information system software platform. Maybe it's just visualizing a digital map, or maybe it's selecting data that's out there already. We want to have data out there in as many ways as possible so that the public can use it and industry can use it to the greatest extent possible. To start, what is topography? When I use that term, why do I use it and what am I referring to? A lot of different people make maps. A lot of different people make different types of maps. People use Google Maps every day. You want to know when Starbucks is open, how am I going to get to my kid's soccer practice, where is my date going to be tonight? That's something that maybe Google Maps is really spectacular at, understanding where all the different retail establishments are and routing. Maybe not so much the topography, where they're trying to map the natural and artificial features of an area, things like mountains and rivers and streams and coastlines. That's really where the USGS comes in. And in many cases, some of those commercial map providers like Apple Maps or Google Maps, they use our data, and that's where it comes from. A big part of what we do is providing data that's out there for free, so those applications really don't have to go recreate that data. They have authoritative data that the government's already spent funding on, and they can leverage it to help all of those other consumer applications. But when I talk about topography, and this is what my program focuses on, we're talking about mapping mostly the natural features. We do add in some administrative features and built features, but this is really what we're focusing on. Why do we map topography? Well, first, it's just exciting. I think so, and it's been driving exploration, and it's a reason for exploration since people have been doing it for thousands of years. There's a picture there of the world's first map from 600 BC. So maps have been around a long time. It's just the way people record information in a spatial way. If you bring a map to a table with friends or family members and we're planning a trip, it's a conversation starter. It's just something people like to do and a way to represent their knowledge of the world around them. We also map because we're told. In this case, we have direction from Congress. When the U.S. Geological Survey was stood up in 1879 through our Organic Act, they directed mapping efforts to be completed. In that case, it was an economic driver, and it still is. We map to support other economic activities. In the early days, there was westward expansion and mining, the Transcontinental Railroad. All of these things required mapping. It was a bit unexplored, and people needed to know what to expect if they were going to be putting in a railroad, or where they might want to look if they were digging a mine. Now, geospatial services, as we call them, location-based services, there could be, how FedEx knows to route from their distribution center to your front door, how a Uber Eats driver knows how to get you your food, how Google Maps can route you from different places. All of the geospatial industry that we're a part of, where we collect imagery or other types of data, that's a $1.6 trillion economy. It's really remarkable, and it's been wonderful in my career of about 20 years, fun to see that grow from where it was in the 2000s when I started. Also, it supports travel and recreation. People want to use maps so they can they can go around the country and they can explore parks, they can hike, they can camp. They want to know where the boundaries of different places are. There are all sorts of different good reasons. And there's really, this is important when you're dealing with a disaster response effort. You want to have commonality. If you have a number of different people that are all operating in the same area, you need to make sure that they're looking at the same information and referring to it in the same way. It does no good if people are referring to a hill or a river by two different names. Who does all this mapping? Well, it turns out it's quite a lot of people. The government does, the civil side of the government, like the U.S. Geological Survey, and a number of my federal partners at the Census, at NOAA, at all over the place, Forest Service, Natural Resource Conservation Service, also the military side, all of the services, the Army, the Marines, the Navy, the Air Force, the Coast Guard, they do their own mapping products. The National Geospatial Intelligence Agency produces maps. There's a number of different military applications for a variety of reasons. Sometimes it's intelligence, sometimes it's for training on their own lands. And then, of course, federal, state, and local governments and tribal governments will also produce their own maps for their own purposes. Oftentimes, they'll leverage data that comes from other sources, but they will produce maps that might suit a particular need. Industry has a significant role to play. Oftentimes, they are the ones that are collecting the data. It could be imagery or mapping a road or collecting some other satellite information. There are software companies that help us produce the maps. There are surveyors that go out and make sure that that data is valid and verify that it's in the right location, and we're living up to that, one of those A's, and being accurate. And of course, there's private cartographers that help in making the maps and sort of the artful side of this process. And in academia, there's people that are creating new instruments to gather information about the surface of the Earth. And there's researchers that are looking at different ways to analyze data for more mapping information. So there's quite a large community and growing community that are all about topographic mapping and geospatial information. How do we map topography? This is what I'll spend a significant part on this evening. We do it in a variety of different ways. To set a little bit of historical context, when mapping in the United States first began, it was rather slow. There were surveys that would go out and spend quite some time. It was very manual, methodical, produced some stunning maps at the time. And oftentimes those maps were the source for other data. The map might get done and people would pull different parts of that, maybe the hydrography or the contours from that, and that was really where the data came. Now, much of what we do is digital, of course. It's from satellite information or from airplanes that are collecting information. It's all digital. All of our mapping is digitized. We don't do hand-drawn maps, at least not at the scale that we're doing them today. And now maps come from the data, and I'll go through how we turn that data into maps a little bit later. But that animation you see, there's a really good example. That happens to be a NASA sensor that's a simulation of it flying over Florida and capturing information. And that's the kind of ways that we can turn observations, in this case from satellite, into data and then into maps. USGS does have a long, rich history, and it's something that we are quite proud of, and that I am particularly proud that I get to help continue this legacy. It started in the 1870s with what we call the Great Western Surveys. Now, I will fully admit I am not a historian. I like to be a scientist, so if you really want a history lesson, there are other sources. So, but I'll breeze through this to give you a little bit of a context of where we're coming from and where we're going to and where we are now. So there were these Great Western Surveys that helped with western expansion. They looked at in Nebraska, the 40th parallel for the Transcontinental Railroad, Rocky Mountain region, and some of the great geologists at the time. John Wesley Powell was part of these surveys, and in fact, he just recently had an anniversary of his survey last year, which was really great. And our prior USGS director was happy to contribute in a celebration of that. In 1879, USGS was charged with the classification of the public lands and examination of the geological structure, mineral resources, and products of the national domain. And Clarence King, as pictured there, was selected as the first director. Following that, topographic mapping really came under its own efforts with John Wesley Powell. And those two names, John Wesley Powell and Clarence King, are very well known to people at USGS today. These are names we know well. For a long time, John Wesley Powell's desk was in the lobby of the building when you came in. It was really interesting to see that legacy carried out today. John Wesley Powell understood that topographic mapping was really required if you wanted to do geologic mapping. Understanding how the surface of the Earth moved and how it was mapped really influenced where you're going to see the geologic formations and mining and other minerals exposed. In the 1930s, we added aerial imagery, mostly after World War I, when people were becoming more familiar with that. And there were cartographers that had some skill with how to collect the imagery, interpret it, and turn it into mapping products. In the 40s and 50s, we produced 1 to 24,000 scale maps, which is the same scale we produce today. And that's sort of the zoom level, you can think about it. In response to, we did this in response to requests for more detail. People wanted higher resolution, sort of zoomed in maps. So we worked on at the time on how we might be able to support that. And we also contributed to a lot of technical achievements. We have been and still are a leader in the geospatial and mapping and cartographic fields. In the 1960s, we developed ortho-rectified aerial photographs. And what that really means is an aerial image that has been changed and modified to make sure it fits the surface of the Earth correctly and you're not seeing a lot of distortions or anomalies, and make sure it's an accurate picture and not one that just looks kind of weird and doesn't really line up correctly. So if you look real close at that graphic on the upper right, on the left-hand side of it, there's a line that's going from sort of northwest to southeast. and it's kind of a little jagged in the middle with a hump. And on the right-hand side, that's been rectified so that line is actually straight like it appears in real life. Moving forward into the next century, in 1976, we completed the first digital elevation model. That's a way of taking elevation data and turning it into a representation the computer can understand. Sort of like a photograph, but instead of, but it's really a photograph of the elevation, where every part of that picture, that pixel, has an elevation data measurement. We worked on how to accelerate mapping and do mapping at scale and do it at different scales for people that might have different applications. And in the 70s and 80s, we converted different data layers, in this case, transportation and hydrography, from maps to digitized data to support the 1990 census. And in fact, Census Bureau and USGS were the first agencies to really produce digital geospatial data for that 1990 census. And we have a long-standing partnership with Census that we quite enjoy. And we produced in 1987 1 meter resolution ortho-rectified imagery for the lower 48 states. That means that every pixel was 1 meter in size, about 1 yard, and that was really substantial. USGS was a great leader in these what we call digital ortho quarter quads, and it was just a great service for the nation. Really proud to have done that. In 1991, after about 40 years, USGS completed the first series of 1 to 24,000 scale mapping of the United States. That's about 55,000 maps. So I want you to keep that in mind. That was about 40 years it took us to complete a once over 55,000 maps. In the 90s, we worked on completing national scale data sets for elevation and hydrography. In 2001, we launched the digital map, which was the digital way of representing and delivering a lot of these information products in partnership with federal, state, local, and tribal data sets. And in 2009, we started an all-digital automated, semi-automated production of that same 1 to 24,000 scale mapping series. What took us 40 years the first time around takes us about 3 years now. We've really accelerated, so we can produce about 1/3 of the United States every year, and that means we can take, it takes about 3 years to cover the entire United States. So what are in these maps? Well, there's lots of things. It starts with the map elements, and these are going to include things like the north arrow that maybe is a little, also shows the magnetic north for people that really want to use the map, not just for visualization, but might want to navigate upon it. It's going to show you the scale. It's going to show you some other information. The projection, which is a technical term for how the map was really created so that it fits the surface of the earth correctly. And a lot of technical information for people that need that level of accuracy and understanding. There's the projections and grids. This is a way where people can reference the latitude and longitude and help figure out exactly where they are. Geographic names are on there, and there is an authoritative data set that I'll talk about in a few minutes that shows people what are the names for the features that you're seeing. It could be a town, it could be a river, it could be a summit. There's a number of different structures that we include on the maps. In this case, it's, I believe, a fire station and schools that you see there. There's transportation features, there's roads, trails, railroads, airports, all sorts of different things. We work with the Fish and Wildlife Service to help maintain a wetlands data set, national wetlands inventory that shows up on these maps. There's hydrography features that, again, I'll explain. That's an emphasis we have at USGS, and I'll explain much more about that data set in a few minutes. We have the terrain data, the topography. We have contours. We have what's called a shaded relief, which is a different way to represent the elevation. It's sort of, if you were to look at the sun from a particular angle, this is what you would see. It would be shaded and helps really emphasize the elevation, helps you understand what you're looking at a little bit more. If you have a little trouble reading contours, it's just a different way of representing the elevation in terrain. We have woodland, that's the green part there, so you can see where there's wood cover, and that comes from other data sets, like the National Land Cover data set that's built from satellite imagery. We have boundary information, which are the jurisdictional boundaries. Could be counties, it could be states, it could be other things. Those are included. Every one of our topo maps, all 55,000, come with an image base, so you can see actually what the actual image of that ground is and what it looks like, not just a representation through all these features, but actually an image. And then we have a barcode down there in the bottom right-hand corner, and this is a really a rather new development within the last maybe 5 or 6 years. What this allows us to do is to register each map with some of our partners in the Department of Defense, in this case, the Defense Logistics Agency. That means that if there is a need for a mass distribution of maps, to support humanitarian assistance effort or disaster response. And there's a National Guard unit that needs a number of maps for rescue and recovery, like after Hurricane Harvey. They can request a map from the Defense Logistics Agency, and our partners at DLA will print the map and deliver it within 24 hours. And they'll print like thousands of them. And we've done that a few different times since we've instituted these barcodes, and every one of our maps has these. And it's really a great way to leverage this resource so that our partners that are out there and need to help people and need to have maps, authoritative maps in their hands really, really quickly, don't have to waste time. And they have a paper map that they can rely on. There's a number of data sources that all of these data come from different places. And we work with partners all across the federal government to gather that data and aggregate it into a consistent data source, into our databases and into our maps. We get them from, sometimes we produce it ourselves. I mentioned Geographic Names and elevation and hydrography and the woodland layer. Those are all data sets that the USGS has. We have other partners in the federal government that we partner with. The image base that I mentioned comes from a program called the National Agricultural Imagery Program that's run by the Department of Agriculture, but has contributions from a number of different agencies. They fly the entire country and they produce those images. We help them fund the effort, and then we get the data on the back end for our topographic mapping, and we can help deliver it to the public. We have a number of different data layers that you see there that come from our partners in the federal government. And in some cases, if it's not available, or if industry has it, it's just easier to go out and purchase it and make sure that we have the right license so that we can deliver it to the public through our products. But we end up being an aggregator from a number of these different sources to be able to produce a high quality map that fits the needs, the general purpose needs of the public and a lot of our partners. An interesting one that I'll point out there is a national structures data set. We rely on actually a citizen science effort. There's a few thousand contributors that are public citizens, and anybody can join, that help make sure that data set is robust and accurate. They'll help us make sure that the points are actually where they should be on top of the structures, and that the information about those structures, the attributes, it could be the correct spelling or the address, that's all correct. And they produce really high quality data, and we're very happy to have them contribute to our structures data set. There's a couple of programs I want to talk about more in depth because they're efforts of ours right now, priority efforts of ours right now, and they're really interesting to cover. And I think it's just fun to see how we turn the data, how we collect the data and turn it into a map. For the elevation data, where do those contours come from, and how often do we repeat it, and how accurate are they? Well, we have an effort right now called the 3D Elevation Program, 3DEP, that aims to collect enhanced elevation data in the form of high quality light detection and ranging. That's a term called LiDAR, over the entire United States, Hawaii, the US territories, within an 8-year period. It's a really ambitious goal. And when I say it's high quality, I mean super high quality. This is about the best data that you can get without actually going on the ground and visiting every square meter yourself, which nobody really wants to do. And right now we've got about 75% of the country, including Alaska, covered. We use a little different instrument in Alaska, but for the right now we've got about 75% of the country that has enhanced data. LiDAR in the lower 48 states, Hawaii and the territories, and a radar-based instrument in Alaska. What is LiDAR? It's an instrument, and it looks kind of like that one. In fact, that is an actual LiDAR instrument in the bottom right hand by a manufacturer called Regal. It's about 30 inches in height. It's an oversized coffee can type of thing that looks usually straight down from an airplane. And it shoots lasers. It shoots lasers really fast and really often, a couple 100,000 times a second. And there are sensors in the plane that measure how long it takes that every laser pulse to shoot back or shoot down, bounce off of something and come back. And oftentimes it might bounce off a few things and get split. But the sensors are smart enough to understand what light is coming back and when it's coming back, so they can turn that into a map, because they know how fast the light was traveling, the speed of light, and they know how long it took part of that light to come back. They do this very, very fast over wide areas, and they can turn that data into what's called a point cloud. And that's what you see here on the upper left, where they're mapping in incredibly high detail what an area looks like using this method. And this is probably millions and millions of points that you're seeing just in this area here. Our standard is we typically shoot for at least 2 points every square meter. And these are These are measurements. They're not estimations. They're very accurate, and that gives us a lot of very high quality measurements that we can rely on. We can look at the canopy structure of forests. We can look at the sides of bridges. We can look at landslides and hydrographic features and volcanoes and all sorts of fun things. Here's a couple of examples. When we turn that point cloud into what we call an elevation model, it's just a processing step that kind of looks at the average elevation data and turns it into something more recognizable as an image. It gives us a really, not just a beautiful image, but one that's very useful from a scientific perspective, because they are measurements, it's data. It's really great. People can measure upon it, they can do analysis upon it to understand how the landscape has changed, or how it might take, or how long it might take to get from one place to another, what the slope is, how the sun's going to shine on an area just the right way. There's lots of different applications for this. It's a significant improvement when we look at 1 meter resolution elevation models that we're producing from this program. This is upgrading from what is out there now that's 10 meters that you see in the lower left, and that means that every square that's part of this image is 1 meter in size as opposed to 10 meter in size. It's really fantastic. That's the term we use for resolution, and just beautiful images. Here's another example that shows the level of detail we're able to get and how much we're improving over what's out there right now. You can see features, you can understand features that you really never knew were there. And we don't do this alone. We have a number of different partners. Since 2015, we've partnered with 18 federal agencies and over 250, or about almost 250 state and local governments. These have all contributed funding to us to go out and make sure that we can collect this data, and then we host it, aggregate it, deliver it back to the public, so everyone can enjoy all of the contributions that these people have made. And it's really exceptional. It's not often in government you get to see this level of cooperation and collaboration between so many partners at so many different levels of government, and it's really fun to be a part of. And every one of these partners has a story about why they want it, their application, and oftentimes they're very different. It could be for water resources, it could be for a forestry application, it could be that they're building a new highway, and that's a fun part of the job too, is understanding just how these people are using the data. So we spent a lot of time doing this. It's not cheap, it's a lot of money. Is the juice worth the squeeze? Why are we doing this, and is it of value to the public? Well, that's actually how this program started. We set about in around 2011 or 2012 to understand what would be the value of this kind of a data set to the public. We called that study the National Enhanced Elevation Assessment. And to provide that justification, we surveyed a number of different federal agencies and states and other partners to determine how valuable they thought this data would be and what kind of data they did need. And it turns out that the ideal program to maximize all these benefits costs about $1 billion, number one. That was something. And we determined that that best sort of bang for the buck by that chart that you see in the middle. We looked at all the different ways to get the data. We could do it every year at a super high quality level, or we could do it 25 years at a really poor resolution data that would be cheaper. And we found out that if we shoot for the middle, about 8 years at a moderate resolution or moderately high resolution, that would satisfy the most benefits that our partners were telling us they needed and the most requirements for about the least amount of money. But it still cost about $1 billion to collect that data level data for the whole country. Now, we're a rather small program and a rather small bureau, so that's why we needed all those partners. We just can't afford to do this ourselves. The other interesting thing is just how much this returns. So I mentioned that that's about $1 billion over 8 years to collect the data. The other thing this National Enhanced Elevation Assessment told us was this returns to the country every year in benefits somewhere between $1 billion and $13 billion, depending on how it's used. So you get that return very, very quickly and in perpetuity, which is great. And that really validates why we want to do something like this. And the business cases are from flood risk management, and turns out FEMA, the Federal Emergency Management Agency, is one of our biggest partners. They use this data to update their flood hazard maps, to infrastructure, river and stream source management, and even land navigation and safety. When this was completed in 2011, 2012, it wasn't quite yet known how the autonomous navigation industry would use something like this. And that's why there's quite a range there from conservative to potential benefits, but it is actually a use and an application that we're proud to help partner with. So it's really, I think the juice is worth the squeeze. I think we proved it, and it was really, it's great to have that level of validation. And in fact, that's turned into a best practice, and we do it with a number of other data layers now too, to make sure that we're still providing data that's relevant and useful and is a good value for the public. An example of that is what we're doing now with hydrography and our national hydrography data sets. Our NHD represents the nation's drainage network. This is the surface water of the United States, the rivers, streams, canals, lakes, ponds, glaciers, coastlines, dams, and stream gauges. However, it's not just blue lines or things, what you would see on a map as a blue line. It's a lot more than that. It's really a connected hydrographic network that is really rather sophisticated. One of the things we do is we break down all of those stream features into little segments that we call reaches. Each one of those reaches has a very unique address, much like your street address. That means that I can, with one code, I can refer to a very small segment of a stream. It's really useful if you're collecting data about that stream. Maybe I'm counting fish, maybe I'm doing a water quality measurement, maybe I've produced a report about the sediment that's occurring in that particular area. That can all be tagged by that one stream reach code. It's a great way to organize and aggregate data about the river and about the river system itself. In addition, we want to know, where does the water that's in that river come from? Those are called catchments, and we also organize that. That's sort of the lower center colorful graph you see. Those are the catchment areas. Every stream reach has an area into which all the water that falls there will flow into the river. And we code those and understand those. And that is really how you're able to do some sophisticated modeling. If you have an understanding of the precipitation, a rainfall event that occurs, and you know where it's falling on the landscape, and you know which parts of the landscape are flowing into which parts of the rivers, and where those different parts of the tributaries are meeting other rivers, you can model an entire event. And by event, I mean an entire rainstorm or hurricane. And that really helps people understand where there's going to be water availability, where there's going to be an excess of water in terms of a flood, where there might be a drought. So some other attributes that are included in this that makes it a sophisticated system are the flow direction. We know which way the river is flowing, and we can tell each stream reach which way it's going. And that allows for some navigation so that we can trace, for example, if there's a contaminant, if there's an event where there's a factory or something else that ends up leaking contaminant into the water, we can trace where that goes throughout the river system. The specific data product we produce is called the NHD Plus High Resolution. That's our highest resolution hydrography product. It includes the mapping of the rivers and the streams and the watershed boundary data set, which are those catchments. It's based on it uses the elevation data for the catchment areas, includes flow direction and these accumulation surfaces, which is a fancy term for how much water falls where. And it adds all those attributes for stream navigation and analysis and enables a modeling of the water flow. And here's a really good example of what I mean when I say water flow. This is a national water model produced by the National Weather Service. They do this operationally all the time, and they use our national hydrography data set to do it. What you're seeing here is actually a little bit older. It's in 2015, but this is a precipitation event that moved from west to east across the United States. And those different colors are showing the stream flow, the cubic feet per second that occurred at different parts of those streams, where it's, it looks a bit like the country breathing, which I find really exciting. But it also is a great way to show or a real application of why this data is useful. This is something that's really impactful for the National Weather Service to understand where there's going to be flooding and to understand ahead of time so they can get that information out to the public. So again, is the juice worth the squeeze? Is it really worth all the effort we're putting into it? Well, we did another study, a hydrography requirements and benefits study. We documented 420 mission critical uses with a number of different partners once again, and we found that there was over $1 billion total annual benefits. And that really gives us a justification for continuing to upgrade the hydrography data like we do and make sure it's available in open ways that people can use and access and build into their business processes and make smart decisions. There is a growing demand. So we're moving from where we have been in the past, where we have an NHD Plus medium resolution product that supports the National Water Model, to our higher resolution product that's at a much greater scale. And I want you to focus on that bottom number for a second there, and the number of features. And those are the hydrographic features, the water features, and stream reaches that you see. In the medium resolution product that's part of that National Water Model, there's about 2.5 million features that go into that. And we've produced the National Hydrography Plus High Resolution data set, that's an order of magnitude more features that are included, much higher fidelity, a much greater scale, sort of zoomed in if you want to think about it that way. And those are just fantastic data sets. And that one's so great that the modeling on that can't be done yet. They need to build some models to be able to support that data set. Where we're going is actually using that rich LiDAR data set that I talked about for the country and getting the hydrography from that. We call it deriving it, where we can actually pull the hydrography data out of the terrain. We spent a lot of time and effort collecting it, and we might as well use it. And when you do that, that's going to increase the number of features another order of magnitude. And that's where we're going in the next 5 or 10 years, is to see how we can derive the hydrography directly from that LiDAR data to produce just a fantastic data set. It'll be something that no other country can really enjoy at the scale. Another data set that we spent a lot of time on that is just, I find really interesting, and I didn't expect that I would find it so interesting when I joined USGS, is geographic names. I don't know that any of you have spent much time thinking about how different features around the landscape get named, but there is actually a process that is quite fascinating. And it's been around for a long, long time. And there is some authority. There's a public law that states the Secretary of Interior shall promulgate in the name of the Board of Geographic Names decisions with respect to geographic names and principles of geographic nomenclature and orthography. And in case you wanted to know what orthography was, I had to look it up. Orthography is really how you write a language, to include the spelling, the hyphens, capitalization, word breaks, emphasis, and punctuation. And in fact, the board on geographic names that has been stood up dates back to when the USGS was first created in 1890. Turns out just this week, there was a first report from the US Board on Geographic Names in 1890 and 1891 that showed up on eBay. You'll be sad to hear that it is no longer for sale because I bought it and it's showing up at my doorstep next week, and I'm quite excited. Now, there is a Board on Geographic Names that meets every month, and they have since 1890, and I'm lucky enough to be the Department of Interior member that sits on that board. The Board on Geographic Names has a domestic names committee that's mostly focused on the names within the United States. We have a foreign names committee that looks at standardization of names across the globe with other naming authorities from different countries. There's the executive committee that helps run it. There's some special committees on Native American names and communications. And then if we have subject matter experts that help advise us on undersea features and Antarctic features. With the Domestic Names Committee, in red are the ones from the Department of Interior where the U.S. Geological Survey fits. We have a number of different partners. You'll notice that most of these are what we call land management agencies. They have ownership of different land, like Bureau of Land Management or Fish and Wildlife Service or the National Park Service, that different geographic names are on their land, and that's why it's important they're part of this board. And then, of course, we have a number of other partners that are really anybody that has an interest in producing a federal map or understanding of a federal name, like the Postal Service. And that is really what this board does. It standardizes names for production on federal geographic products and maps. We have a number of different policies. We don't vote on a name if it's pending in Congress. And you might wonder why that is, or why does that matter? It's a really good example, and it's the tallest mountain in the United States, what was Mount McKinley and is now Denali. McKinley was president from Ohio, and there was an interest from people in Alaska and others to name Mount McKinley, rename it Denali. For a number of years, the congressional delegation from Ohio would put in legislation to make sure that that name stayed McKinley. It didn't go anywhere, but every Congress they put in a new bill that suggested that name not be renamed. Because it was pending, even though there was no push, we were not able to take up that name change, even though there were a lot of local Alaskans that wanted the name change. And turns out that was actually in 2016, I think it was 2015, Secretary Sally Jewell at the time of Department of Interior did make that name change by secretarial order because the Board on Geographic Names, since there was pending legislation, we couldn't act on it. So that's a really great example of where we cannot act if there's pending legislation and why. We need a compelling reason for changing a name. We don't just do it willy-nilly. There's got to be a reason and a justification, and that the name meets all these other policies. You can name a feature for somebody or rename a feature for somebody, but they must be deceased for at least 5 years. We'd like to see that they have an association with the feature or made a significant contribution. Maybe it was land that they owned or they farmed or they visited often, or there's all sorts of reasons people can have a connection to a particular geographic feature. There is a wilderness area geographic names policy. One of the great things about wilderness areas, and you learn this as a Boy Scout or Girl Scout, is you leave no trace. We follow the same philosophy with names. We don't apply new names in wilderness areas. We will rename a name, but we won't put a new name. There are a number of derogatory and offensive names actually in the country right now, and we encourage changes to any name considered offensive by an individual or group. The eye is in the beholder. We're not ones to say what is offensive or what is not, or what is derogatory and what is not. Different groups of people will view that differently, and we'll rely on them to provide us a justification for why they think a name might want to be changed. We have a policy for diacritics. These are things like umlauts and all sorts of different features that occur in different alphabets. We just need to make sure that they can be rendered by a keyboard and shown up in a database. We have a policy for duplicate and similar names. It doesn't really make much sense to have duplicate names near to each other. If there's 6 rivers all named Clear River in the same county, it can be a little confusing, and there's really no purpose from a consistency and standardization perspective. Names have variants, and in fact, what you see here is Devil's Tower in Wyoming, and all those names on the right-hand side are variant names. In the database that we house, the Geographic Names Information System, you can search by variant names so you can understand what all of those are. And maybe you use a variant name as opposed to the name that is the formal accepted name. It also provides a historical record. You can see how the name was referred to or how it changed. We have a policy on long names. We really want to focus on having last names only and not full names of people. And we have an extensive policy about how we deal with tribal geographic names. And that's we want to make sure we understand our trust responsibilities with tribe and take care on how they approach their naming responsibilities. Commercial names is another really interesting topic. There might be a number of different reasons why companies or industries might want to rename a geographic feature. Maybe they want to have Coca-Cola Mountain or Pepsi River. That's not something that we believe should be allowed. We don't want to be seen as endorsing business or commercial products. And here's a few examples of ones that we, in some cases, we did approve and other ones we didn't. Tyson's Corner is a commercial center here in Northern Virginia. It's an unincorporated city, so it falls under the purview of the Board of Geographic Names, and they desire to change their name from Tyson's Corner to Tyson's. There was some thought about the commercial implications, but in the end, the board voted that we could approve that name. The Rotary Club, many of you might know that association, they wanted to name a peak in, I believe it was Colorado a number of years ago, and that was one we did not support because it was directly linked to that club and their efforts. And of course, some people might want to name their features after pets or other animals. Only in rare instances would we allow something like that. We do have a database of that we house all these names, and when there's a name change, it goes into that database. It was developed 40 years ago and has over 2.2 million features and includes all of the physical features and then also some administrative ones. And this is the authoritative names for all federal products. If you're creating a federal map or any other product that needs the authoritative federal name, this is where you go to get it. There's a lot of information that's historical, that's very, very valuable as an archive and a representation of how we viewed our landscape over the years. Here's just a couple of examples that show up when you go and search for a geographic name. I did want to talk quickly about governance. With so many actors producing so much data, you can wonder how we're all connected. And indeed we are. There's a Federal Geographic Data Committee that's a formal structure that links all of the federal entities that collect geospatial information. And they manage it like a portfolio, where they've identified a number of framework data sets in yellow and a number of other supporting data sets there in white. And they've assigned a government agency lead for each one of them. And in fact, I'm the lead for elevation and water inland, since we manage the 3D elevation program and the National Hydrography data set. However, that might, under that theme, we have a number of other data sets that could come from somebody else. Maybe Department of Homeland Security or the Forest Service has an elevation data set that they maintain that's really important. We include that as owners of that theme. Overall, there's 18 themes with 173 different data sets. And these are all organized to make sure that we're not stepping on each other's toes, that there's cooperation, there's sharing, we're not banging the same data twice, and everybody is really connected and coordinated to make sure we're spending the data wisely and sharing it like we should. Where are we going in the future? There's a lot of different players, particularly industry. What is the place for the state and the government when we're looking at innovation and delivery and science and research and building the next generation of products? There was a British economist, John Maynard Keynes, who had this quote here that I really like, and it was compounded upon by Mariana Mazzucato, a European, a contemporary one, she's around right now, written a book called The Entrepreneurial State, and she has a great TED Talk out there where they talked about the important thing for government to do is not to do things which individuals are doing already and do them a little better, a little worse, but to do those things which are not present done at all. Things like a national elevation data set. I think that's a really good example. We're also producing, in that effort, a dynamic mapping process where we can allow people to come into our topographic mapping archive and create a map where they want it. To do that, we have to make sure the data can adapt to how different people might want to call upon it. This is a quick graphic that shows different hydrography data at different zoom levels, if you want to think about it that way. If you want to see a hydrography feature at one zoom level and I want to see it at a different, that data needs to know which one to draw to. And we built that intelligence into the data, which allows for dynamic mapping. We've also built intelligence into the data so that everybody who likes maps knows that the most interesting thing is that the seams of different maps. We're building a system where you can drop a point anywhere you want and have a map built around that with the features that you want at scales that you might be interested in, not just the only data they exist at. That's what we're referring to as dynamic mapping. We're hoping to release this to the public at some time in the future. And that'll be quite a different shift from how we produce our products now, which are the standard scales that you're used to seeing, only at those scales and only at the center points where we have them. We're going to be moving to something that might fit how people want to use that data more. We have a great concept for how we're linking data on the landscape with data at the coast and data in the ocean called 3D Nation. We have partners in the National Oceanic and Atmospheric Administration for that. And we're building this concept called the 3D National Topographic Model to understand how we can model everything from the highest mountains into the oceans, the depths of the oceans, connected to groundwater, to engineered systems like stormwater in urban areas, and research different ways of representing that data so people like the National Weather Service can build upon it and create better products for people to save lives and property. I did want to make sure that people understood we do our level best to make sure we deliver the data out to where people can get it. We do that through stage products like the paper maps that you're used to. If you are a sophisticated user, you'll know what a web mapping service and other services are that you can integrate right into your platforms. And there are other software development terms or ways of, if you wanted to leverage our data in a software development application or web map, you can do that as well. The national map, nationalmap.gov, is the main way to get our data. So please do visit and make use of the programs and let us know how it's going. And we do work very hard to continue feeding the geospatial appetite. There are a number of different applications that are out there right now. We want to make sure we support them, from landslides to volcanoes to all sorts of different things, flooding. We want to make sure that we are delivering data that meets the needs of the public to keep everybody safe, save lives and property, and build on the national infrastructure and a number of different national priorities. And I will leave it there.
Okay, Mike, thank you so much. You covered a lot of really great materials there. I think now at this point we can go ahead and open it up for the Q&A. We did get a few questions that came in. So let me start with the first one here. This one came in from Paul. He says, this may be described in the talk, but I was curious on where the elevations listed on Google Earth are coming from. Is that from USGS data, and are they reliable?
I would say they're almost certainly coming from the US Geological Survey. I would say they should be reliable. It's hard for me to tell without knowing particularly what data you're looking at or what data set it's coming from. But if Google Maps or anybody else is really looking for an authoritative national scale data set of elevation, they're going to have to get it from the USGS. The data might be a little bit older, and it depends on what reliable means. One of the more popular data sets that's out there right now was flown in the early 2000s from actually a space shuttle, but the accuracy isn't real good. It's not like we have LiDAR now. If you're gathering elevation data from LiDAR, it's going to be much more accurate. So I guess to answer Paul, the data is probably from USGS, but the reliability or the accuracy of it might depend on what the source of the data was.
Okay, great, thank you. Another question that came in, excuse me, this is from Leon. Does the purview of this data include underwater topographical maps as well, or is this maintained strictly for land masses?
Great question. That term for underwater topographic mapping is called bathymetry, when you're actually measuring the elevation beneath water. It could be inland in a river or a lake, or it could be in the coastal or oceanographic sense. We absolutely do that as well. And we partner with NOAA and the Army Corps of Engineers for mapping some of those things. And we've actually got some pilot areas right now where we're mapping both of them at the same time. So we can fly one sensor that's able to map over the land and over the ocean, and we can create a seamless elevation product that goes underwater and back up again to land.
Okay, great. We have one on here that I'm just waiting for a little bit of clarification on, so let me move on. This one says the new US topo maps seem to differ a little bit from the older USGS topos. Will the older topos remain available, and will the new maps eventually have all the data that the older ones do?
That's a great question, and we get that from time to time. I'm not anticipating that the historical topo maps are going to go away anytime soon. They're a really popular product. We see that in the download rates all the time. And they're a great archive for people that really want to know how the landscape has changed. There's a reason why the data is not the same. When we, in 2009, stood up the automated system, we had to make some sacrifices. In order to have a frequency of mapping and the scale of mapping that we did so that we could turn over maps pretty quickly every 3 years instead of every 40 years, we had to sacrifice some of the quality aspects. We wanted to have a product that was more responsive. We could have the same level of accuracy if we had hundreds and hundreds of cartographers that were able to walk the earth and really describe the landscape the way they did over 40 years for their historical topo maps. In some ways, to answer the second part of that question, will they be as accurate? I think it depends. The LiDAR data that we're collecting will surpass any accuracy of the contours that were on the historical topo maps. Some of the data that was on the historical topo maps, like mine locations, we may not be able to reproduce. So it's another one of those ones where it depends. The hydrography and elevation we're able to do in far greater detail now than on the historical maps, but some of those features that are on the historical maps they might remain as the most authoritative source. And we want to harvest those where we can and reuse them, and in some cases we have. In other cases, we're going to build upon it the best way we can.
Okay, great. Another one just came in from Alan. From what sources do most inquiries, actions for the BGN come from? Examples are derogatory names, new names.
They all come from the public, from citizens like anybody that's listening. Anybody can submit a proposal. If you have an interest, lots of times there are people that have a connection to the area around them, or maybe we've gotten ones from high schools that want to name a feature for their high school mascot. We've gotten ones where there's a historical figure that they would like to recognize for their importance in the area. Other people, they hike in a particular area and they know there's no name for a summit or a crag, so they want to put a name to it so it's more recognizable. They come from all over the place, from all over the country.
Okay, great. One more I'm seeing here. You mentioned volunteer opportunities to update structures. Do you still need volunteers, and how would one find out more or apply to help out?
Yes, we were happy to take volunteers. If you search through the National Map Corps, CORPS, I have no doubt you'll be able to very quickly find the registration link where you connect with us and get signed up.
Okay, awesome. I'm not at this point seeing any other questions come through. So Mike, we thank you again for being our speaker tonight and answering all these great questions that people are coming up with. I also want to thank everybody out there in virtual land for joining us today. Just in case you want to watch Mike's presentation later or share it with others, it'll be available in about a week on our public lecture website. I believe the slide is up there now. And we do hope that you'll join us again next month on May 27th at 7 p.m. Pacific time. Again, that'll be Austin Elliott's presentation on earthquakes. So until then, thank you all for joining us. Thank you again to Mike for being our presenter. Keep an eye out on our website. We'll have Mike's talk archived. We have last month's talk archived, as well as ones from many, many years past. So again, thank you for joining us. Have a good evening and goodbye for now.